In last lecture, we introduced to you the concept of power series, that any series of this form is called a power series, is a power series, and we associated to any power series, we have a disk of convergence. Mm, this is Z naught is the center of the power series, and the center of the disk will be Z naught, and the radius of this power series, radius of convergence of this power series is the radius of the disk of this convergence. And what else properties this disk had, that inside this disk this power series was absolutely convergent, and inside any closed disk, inside this disk, on any closed disk, the series is uniformly convergent. Series is uniformly convergent, whereas outside, for any point which is outside of this disk, the series does not converge. That is, you can call it to be divergent. And on the boundary point of this disk, we cannot say anything. Can't say anything. वहाँ पर पॉइंट्स पे वो कन्वर्जेंट भी हो सकती है, डाइवर्जेंट भी हो सकती है. सो बाय द वे, आपके पास आल्सो हमने ये किया था कि रेडियस ऑफ कन्वर्जेंस के कुछ फॉर्मूले निकाले थे, और रेडियस ऑफ कन्वर्जेंस जो है, it can be a number between 0 and infinity. And note that when the radius of convergence is 0, radius of convergence means 0, you cannot have a disk. This big, you cannot have this disk of convergence. In that case, this power series will be convergent only at one point. That it will be convergent at only at Z naught. It is in this power series is convergent. Is convergent. Elsewhere, it is always divergent. So this case, there is nothing interesting to be talked about when you have radius of convergence equal to 0, but you will see certain power series whose radius of convergence is always whose radius of convergence is 0 also. It is that means there are power series for which radius of convergence is 0. So now what we are going to do now is that I'm going to take the power series for which the radius of convergence is greater than 0, and then we will look at the limit of this power series within the disk of convergence. Because in the disk of convergence, this power series will define a function, because since power series is what? It is a special type of series of functions. And when we say that it is convergent in this disk of convergence, so here it defines a function fz. And in the today's talk, in the today's lecture, we will see that this function is actually an analytic function inside this disk of convergence. So that's why this study of this power series becomes an important thing at it, because it has a relation with the analytic functions. So today you will see a one-way relation, that given a power series, you get an analytic function. And perhaps in tomorrow's lecture, uh, we will see that given a analytic function, we can find a power series associated with that analytic function. What will be the structure of that power series? That will be studied there. So I start to state the theorem that we have to prove today. And the theorem is that suppose this power series. So I'm going to take a power series about origin only, because you can change, you can keep in mind what I had told you in the beginning, that you can always consider a power series about origin with the change of variable. So I'm taking a power series about origin, and suppose this power series has a radius of convergence, r to be positive. Then the limit function fz, which is this function, and it is defined within the disk of convergence, is analytic in this disk of convergence. And it not only says that it is analytic, but it also says that also further it says that derivative of this function of any order exists for k in n, and the formula for derivative of this function fz is given again in terms of the power series, and the power series is what it is, n factorial upon n minus k factorial, where it is better to take n to be greater than or equal to k, a n z to power n minus k, and this is a power series which is again valid here. So this is again a power series. How you going to obtain this kth derivative of this function fz, which is the limit of this power series function? What you will do, you will just differentiate this power series term by term. You just take the first derivative. Look at, if you take the first derivative, that means first derivative of this function will be nothing but it is just n times a n z to power n minus 1, and you just take n greater than or equal to 1, because n equals to 0 लेने का benefit नहीं है, it will be 0 in that case. तो डबल डेरिवेटिव आप फाइंड कीजिएगा. इफ यू फाइंड सेकंड डेरिवेटिव को आपको फर्स्ट डेरिवेटिव को डिफरेंशिएट करना होता है, तो फर्स्ट डेरिवेटिव इज अगेन अ पावर सीरीज. It is n greater than or equal to 2, it will be n into n minus 1 a n z to power n minus 2. In this way you get all the derivatives of this function. And now since I'm using here certain things, for example I'm using this power series, but the thing is that you need to be sure about whether this power series has a radius of convergence positive or not. But let me complete the statement of this theorem, then we will say more than being a positive radius of convergence for these power series. Indeed, we will show that the radius of convergence of this derived power series, the derivative power series, is same as the radius of convergence of the original power series, which represents the function fz. And the final thing that this power series, this theorem will tell you about, that you can evaluate the coefficients of the power series in terms of the derivatives of the functions. Coefficients are constant terms, and it says that the coefficient this is evaluated as a nth derivative of f at 0 upon n factorial. And calculating this is not a difficult thing. You just substitute. Let me use k here also. Let me use k. Otherwise, you might have confusion of notations. You just substitute n equals to k, then you will get this formula for the kth coefficient of this power series. So The first thing that we have to show that this function is an analytic function, and how to show this is an analytic function. Let's begin the journey. Look at this disk. What is a disk? Disk is a domain. And if you remember the definition of analytic functions on a domain, what is the definition of analytic functions on domain? The function needs to be differentiable at each point of the domain. So to show that this function is analytic at each point of the domain, we will just show that it is differentiable at each point of the disk. But before that, let me state a kind of result which I have put as an exercise in notes, but I will write it as a lemma here. What this lemma states? It states that if no, let me write it in a more brief way. The power series, the following power series, एक पावर सीरीज ये ले लेते हैं z minus z naught to power n where n greater than equal to 0. दूसरी पावर सीरीज आएगी, ये पहली पावर सीरीज को डिफरेंशिएट करो, n greater than equal to 1 n a n z minus z naught to power n minus 1. तीसरी पावर सीरीज आएगी n a sorry, it will be n, and फिर से डिफरेंशिएट करेंगे इसको n minus 1 a n. You can begin n from greater than equal to 0 z naught to power n minus 2 and so on. Differentiate करते जाएंगे तो you will have n greater than equal to k. It is n factorial upon n minus k factorial. Just a minute. Yes, okay. aka n z minus z naught to power n minus k. All these power series have same radius of convergence. So what is the relation between these power series? Look at, you get this power series if you differentiate the first one. If you differentiate this with respect to dz, you get that x power series. And we have to prove that these two power series have a same radius of convergence. And similarly, the next power series, this one, just this power series is obtained by differentiating this previous one, and this is the way. So what I'm going to show that these first two power series, which are enclosed in red enclosure, they have the same radius of convergence. That means if the first power series has a radius of convergence r, I will show that the second one also has the radius of convergence r. Then applying the same argument, you can show that these two power series, the second one and the third one, have the same radius of convergence in this way. And let me prove. This is a very simple proof here. So I will show that we show that power series a and z, and also let me take without loss of generality. Let me be, I'm just confusing. Without loss of generality, assume that z naught is equal to 0, so that we are taking the power series above origin. So we show that this power series and this power series a n z to power n minus 1 have the same radius of convergence. So what is the formula? What is the more general formula irrespective of root and ratio test? Because root and ratio test I cannot apply here, because for that I need to have that guarantee that limit of the coefficients, ratio of the coefficients, or the roots of the coefficient must exist. But what I can use, I am going to use the Cauchy-Hadamard formula. The Cauchy-Hadamard formula for radius of convergence is this one: limit nth derivative of mod of a n, reciprocal of this limit superior indeed, this thing. And reciprocal of this, let me write reciprocal in this way. And this is the radius of convergence of the power series first. And what I have to show, I have to show that same is the radius of convergence of the power series second one, which is the differentiated power series of the first. That means for that I need to show that this limit nth root of a, what are the coefficients now? In the second power series, the coefficients are n, a, n. I need to show that these two values are equal, because the second limit on the right hand side is the formula for the radius of convergence of the power series, differentiated power series, this one. And the first one is the radius of convergence of the power series, first one a and z to power, and if these two values are equal, so both will have the radius of convergence to be same. So but let us begin with this limit. Look at this thing. Look at this thing. Let me write coefficients of this power series as bn equals to n times an. So bn to power 1 by n has to be n to power 1 by n mod of an to power 1 by n. So what it implies? It implies that the limit superior but that means, okay, anyways, let us write limit superior of this bn's as n goes to infinity is limit superior of n to power 1 upon n into mod b mod a n to power 1 by n. But we have something noun here, is that limit superior of n to power 1 by n. When a sequence is a convergent sequence, then limit superior and limit inferior are equal, and that those are equal to the value of the sequence. And here n to power 1 by n is a convergent sequence, so it has to be equal to the limit of the sequence. And if you remember, the limit of this sequence is nothing but this is the 1. So if this is the value of the limit is 1, therefore limit superior value of bn has to be equal to limit superior of an to power 1 by n. And this is what we had to prove. And this proves that the power series, this shows that both the power series, first one an to power zn and its differentiated power series n times an z to power n minus 1, have the same radius of convergence. Now next you can apply the same argument to taking this as the first power series, and the second one power series is the differentiated of this power series, and in this way you get same radius of convergence. Okay, we will be using this thing, and now coming to proving that the limit of the power series is the analytic function in the discuss. convergence. So let's go to the proof of theorem. Let me bring the like. So what we just see that it is given to us in theorem that radius of convergence is given power series is R. So by just the lemma that we just proved, that we see that we have from lemma that we just proved that uh, the series this one a n and a n z to power n minus 1, since it is the power series of convergence R, so this is convergent for mod z less than R, and so it defines a function, and so it defines a function, and I'm going to denote this function by g z. It defines a function n a n minus 1, obviously, and you can take n from 1 to infinity. That means with these notations, now we are here to show that this function f is differentiable and its derivative is equal to g of z. We will show this thing for each z in this disk of convergence. This is the disk of convergence. We have to show this thing. So let's begin this now. So how we're going to do this? Let us fix a point where we want to show this function to be differentiable, that is with z, and let us choose another complex number h such that I have to make this h somewhere satisfying this inequality r minus mod z upon 2. Let me tell you why I'm adjusting this thing. I'm choosing this z this way. So what's going to give me this inequality? Look at this thing. Then mod z plus h. I use the triangle inequality. It is mod z plus mod h, and it is mod z plus r upon 2 minus mod z upon 2, and this is equal to, I'm using the inequality that h satisfies, that I just took here. So it is equal to r upon 2 plus mod z upon 2. But again, z you are taking in the disk of the convergence, and there the modulus is less than r, so it is r by 2 plus r by 2 is equal to r. So this gives me that z plus h is also an element of the disk of convergence. This is disk of convergence. You fix some z, and you want a complex number h such that z plus h is again in this disk of convergence. And what is the benefit of having this z plus h in this disk of convergence? Then I can apply f on z plus h. This is now defined quantity. If I take h with that inequality, whatever h I can take. So I needed this thing to be defined. Why? Because to prove that f is a differentiable, and I need this term to be there. Now consider f z plus h minus f of z upon h. So that's why I needed this z plus h to be in the disk of convergence. And to show that this function is differentiable, you just need to show that the limit of this coefficient exists when h goes to 0, and this is what we have to do, and that is the job for us in today's lecture. So apply the power series. So what is the power series? You can have this power series z plus h and greater than or equal to 0. It will be an z plus h to power n minus an z to power n greater than or equal to 0 and whole to h. But n equal for n equal to 0, you will have coefficient a0, and that coefficient a0 will cancel out. A naught minus a naught will cancel out, so you will be having a range of summation from n greater than or equal to 1 left to you, and you just take out the summation outside because it's a convergent series. We can add and subtract the series, so it is here. Now you have this thing an, where n is greater than or equal to 1. Now you have z plus h to power n minus z to power n upon h. You have this thing, where what we are going again to fix things here, because this is your disk of convergence. You have z here, and the selection of z plus h is such that z plus h is again in the disk of convergence. So what we are going to fix, we are going to fix another disk within the disk of the convergence of some radius r, so that I can write here, it is not visible, so that where z and z plus h are such that the maximum of modulus of z and mod of z plus h is less than or equal to r, and it is less than, let's give it a bound, and this is always possible, that as you can see. So now what we have to show, we have to show that fz plus h minus f of z upon h minus g of z, this modulus. But let us calculate what it is. I have calculated this of z plus h, and what it is, it is summation n from 1 to n 1. It is a n z plus h to power n minus z to power n upon h. But again, gz, what is the value of gz? Let me recall. Gz is this power series, whose range is n from 1 to it is a n z to power n minus 1. So this is the same. I can take out this summation and with a n, and what is left to me is minus n times z to power n minus 1. I will have this summation. And if I want this function to be differentiable, I want this left hand side to go 0 as h goes to 0. This is what I have to do this thing, and keep this estimate in mind. We are going to require this estimate again. So, but here we have things to be tackled. We have this number to be adjusted now. I want this thing to be treated. So let us note few things, and then adjust those settings here. First, note this thing. Note that if you have a complex number different from 1 and n greater than or equal to 2, look at this ratio. It is equal to 1 plus alpha square plus alpha to power n minus 1. And if you want to verify, you just multiply your right hand side with 1 minus alpha. You will get 1 minus alpha power n. And if we differentiate this thing, if we differentiate it, what we get, you just differentiate first the left hand side. You on the left hand side you use the quotient rule. And what is the quotient rule is that 1 minus alpha into minus n alpha to power n minus 1 minus 1 minus alpha to power n into 1 minus alpha ka differentiation with respect to alpha. You are differentiating it. It is minus 1. Numerator is 1 minus alpha square. This is the left hand side. Let me adjust first. Right hand side will be 1 plus 2 alpha plus 3 alpha square plus so on so on plus n minus 1 alpha to power n minus 2. And what will be your left hand side? You can further adjust it 1 minus alpha. You can make certain changes here. I mean, it is minus n alpha to power n minus 1. 1 minus alpha you can cancel out, and you will be left with 1 minus alpha. And the other term is minus, and minus it will be plus, and it is 1 minus alpha to power n upon 1 minus alpha square. So what I can do here is that from denominator I can multiply 1 minus alpha to the right hand side, so that I'm left with here. I will not be having this thing. I will be having this expression, and right hand side I will be multiplying this with 1 minus alpha times 1 plus 2 alpha plus 3 alpha square plus so on plus n minus 1 times alpha to n minus 2. So you have this inequality. Now let me rewrite this inequality in a good way. 1 minus alpha to power n, 1 minus alpha minus n times alpha to power n minus 1 is 1 minus alpha, and it is 1 plus 2 alpha plus 3 alpha square plus so on plus n minus 1 alpha to power n minus 2. So let me make certain change here. Replace alpha by z upon w. Think of w is equal to z plus h. This is what we need. So what we are having now, I am going to have 1 minus z to power n upon alpha, w to power n upon 1 minus z upon w minus n z to power n minus 1 upon w to power n minus 1 equals to 1 minus z upon w 1 plus 2z upon w plus so on plus n minus 1 times, I'm going to it is z to power n minus 2 upon w to power n minus 2. So simplify the left hand side first. So what you will have w to power n minus z to power n, and in numerator you will have w minus z, and you will have w to power n minus 1. You will have w to power n minus 1 left, and you have w to power n minus 1 in the second term also. So what you can do, you can take that w to power n minus 1 to somewhere else. Where you want to take, you take that onto the right hand side. You will be having n minus 1 equal to w to power n minus 1, and your right hand side is w minus z upon w, and interior part is same as it is. So what we are left with to simplify. We have to simplify this right hand side again, and this right hand side is again, now you have on right hand side w minus z. The numerator of w minus z is w, and you just adjust this power with w to power n minus 1. You will be having w to power n minus 2, and you are multiplying that w to power n minus 2 uh, inside of this expression. You just multiply that inside here, and what you will have, you will have w minus z, and you will start with w to power n minus 2 plus you will have 2 times and w to power n minus 3 plus so on plus you will have uh, at the end you will not have any power of w, because you already have at the end you have w to power n minus 1 in the numerator, and it will cancel with it. You will have only z to power n minus 2, but you have multiplication of this n minus 1. So let me write the final inequality that we have. We have this final inequality w to power n minus z to power n upon w minus z. I have this w minus z, and I'm having this inequality w to power n minus 2 plus 2 times w to power n minus 3 plus so on. And then actually I have the power with z also with this plus so on plus n times n minus 1. Let me correct here also. It is 2 times w to power n minus 3. You have a z also here. You cannot miss the z here. So it is w to power, no, you don't have no the w here. You have only z to power. You have only z to power n minus 2. So now take the modulus on both sides. W to power n minus z to power n, w minus z, and use the triangle inequality. You will be having w minus z into mod of w to power n minus 2 plus 2 times w to power n minus 3 mod of z plus so on plus n minus 1 mod of z to power n minus 2. But what you know that maximum of mod w and what is this w is actually your z plus h. You know this maximum of these numbers is less than equal to r. So you can write here that this is equal to w is z plus h to power n minus z to power n upon w minus z will be h is less than equal to mod of h, and you bring out this w to power n minus 2. It will be less than equal to r to power n minus 2, and everywhere you replace w less than w mod of w less than equal to r and z also less than equal to r. So you everywhere you will have a power of r to be n minus 1, and inside bracket what you are left with 1 plus 2 plus so on plus n minus 1, and this thing is equal to mod h r to power n minus 2 into what is this sum and n minus 1 upon 2. So we have this thing here. So what I'm going to do, I'm going to use that expression here now. So let me begin from here. Let me replace all those things here if I can. If I have an option to delete everything here. Yeah, I have. Yeah, okay. Let me clear another whiteboard also. Okay. No, let me keep this the way it is. So look at this. Thus this fz plus h minus fz or h minus g of z. This modulus is was actually equal to summation n bigger than equal to 1. It was an, and the bracket was z plus h to power n minus z upon mm, h minus n times z to power n minus 1. This thing. Now use, since the series is convergent, you can use the triangle inequality type thing here. It will be less than equal to summation n greater than equal to 1. It is mod of a n mod of z plus h whole power n minus z upon h minus n times z to power n minus 1, and the estimate for this modulus here, the estimate for this is obtained as to be less than or equal to summation n greater than equal to 1 mod of a n. Yeah, this one is the estimate. Yeah, this thing is there that we just obtained. It is mod of h times r to power n minus 2 into n minus 1 upon 2. This is the estimate. So there are things that you can take out. You can take out mod h upon 2. You do not need to worry about this thing. What is a n r to power n minus 2? Yeah, this is it. Now let's look at this thing. See, I want h to be going to 0, but if I take h to be 0, so where do I find a trouble? I find a trouble here. This is an infinite series. If h goes to 0, this product may not go to 0. This product may not have a limit if this infinite series is not convergent. But the lemma that we just proved, but by lemma, this is a differentiated series. Joe, I just had missed here things. This is here I have n into n minus 1 also. ये भी होना चाहिए यहाँ पर n into n minus 1. But by lemma, this differentiated series, it is convergent for mod z less than equal to r. Whenever this mod z is less than, there is a convergence. So this is a convergent series. If this is a convergent series, that means this implies that this is a finite number. This is a finite number. And if it is a finite number, then you have this limit. Let me take. This implies that this means that this must go to 0 as h goes to 0. Because there is a standard result to you that if you have a function f, another function g, and what it says that if it says that this function g is bounded and f goes to 0 for a certain limit as x goes to some value, then this product also goes to 0. I'm going to use, I just use that value here because you have this series that is bounded and limit mod h upon 2 goes to 0. Hence, everything will go to 0 as h goes to 0. Hence, what it implies that this limit h goes to 0, f of z plus h minus f of z over h exists, and this limit is nothing but this limit is g of z equals to summation n greater than equal to 1 a n z to power n minus 1. That implies that derivative of f at z exists, where z was an arbitrary point in the disk of convergence, and hence the derivative of f exists at each point of the disk of convergence, and this disk of convergence being a domain and this function being differentiable at each point of the domain implies that f is analytic. F is analytic on this domain, and this is the part, and this is the main thing that we had to prove about this thing. Now, another thing is that you have to show that its double derivative also exists. So what you are going to do, you are going to apply the same argument. Apply the same argument to derivative of fz, which is again a power series. You again apply the same argument to this. What you will get that this function is also differentiable. We get the double derivative of this function exists, and it is nothing but just the differentiated series n into n minus 1 a n z to power n minus 2, and continuing in this to get everything. And hence in this way, you what you will get the kth derivative of f at z to be equal to summation n into n minus 1 so on up to n minus k, no, at minus k plus 1, it is n minus k minus 1 into a n, and it has to be z to power n minus k, but this number can be, but look at this thing, you can write this number to be summation n factorial upon n minus k factorial. Is it okay? This thing, this is the number, this thing, and it is a n z to power n minus k, and here summation range you can take n to be greater than or equal to k, because for n equals to 1 it will be 0, n equals to 2, and up to k minus 1 it will be 0, and this is where k can be any natural number. This way you get all the derivatives of all of the all orders of this function fz. And to compute the coefficients, what you can do, you just substitute. I can write this expression as n equals to k से अगर आप इसको start करेंगे, you will have this thing to be ak upon, you will have k factorial, because you are substituting n equals to k, and n minus k will be k minus k 0 factorial 1, and then you can start range of summation from k plus 1, it will be n factorial upon n minus 1 k factorial a n z to power n minus k. And now substitute z equal to 0, what you get? You get this thing, f kth derivative of f at 0 to be ak upon, sorry, it's not upon here, it has to be multiply, because numerator mein hai, so it has to be in multiply k factorial, and it is k factorial, and from here you want the coefficient ak, it is kth derivative of f at 0 upon k factorial. So this is all about limit of a power series. That limit of a power series is an analytic function, and all of its derivatives exist. They can be obtained by differentiating the series term by term, and we can compute the coefficients of the power series also in terms of the derivatives of the function that is represented by this power series. Okay, I stop here. Now I take your questions, queries. If you have, you can ask. बोलिए. You have any questions?
So
नहीं है किसी का? Okay then. See you tomorrow.